and I go, right, one way I can do this is I'm going to split it up into different areas. So maybe, oh, that's my scale is off here. I'm trying to split it up evenly into, okay, so I split up into some areas, and these areas make rectangles. See those? There's 4 rectangles there.
But there are 3.
Yeah, there's only this one doesn't really count. Yeah, but there's and I can estimate that what the area would be by adding up these rectangles. Yeah, but I can also use 4 other rectangles. As in, I could think about, okay, if I do these 4 rectangles, I can definitely conclude something. The area would be between the two, yeah. If I got the area of this rectangle, this rectangle, this rectangle, that's the blue area, that would be too little, wouldn't it? And the area of the black rectangles, the dotted ones, would be too much. But I can definitely state that the area would be between those two, yeah? Okay. So if I went a bit more detailed, same-ish curve, kind of looks the same, from 0 to 2, and I split it up. So this is what we did last time. This looks a bit different, but I just split it up more times. You just split it up a bunch of times, yeah? And got these rectangles, hopefully more evenly spread out than mine. That'd be a better estimate, yeah? So those areas would be a better estimate than the previous one. The more I split it up, the more accurate it is. How would I say the sum here? So we like to use the sigma, yeah, the sum of the areas, which is the what would be the width here? Well, you could use delta x, but let's say we knew how many we split up. Maybe you could say it was 16 or 20 or 200. You can think about it as delta x, yeah? And it's like the y height, the height of each one multiplied by the width of each one. Yeah, height times the width. So that's one way of doing it, the sum, and then you could add up all those separately. And you think then, okay, yeah, if I wanted to do it to an infinite to its limit and have these infinitely small and stuff like that, we already have a way of doing that with the dx thing. And the heights, well, that's just a y value, isn't it? Okay, so it's like the y values then, another way of writing y is fx, isn't it? Fx. And multiplied by dx would be the infinitesimal, the little, if we made those as small as possible. So if these were tiny, like almost like straight up, but they did have a width, but they were infinitesimally small, it'd be dx. But we didn't want to add them up separately. We kind of wanted to shove it into one summation, like, and not add them up all separately. This is very much a series added together, isn't it? Plus, 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 plus. We want to shove something together into a whole. What's the word for that? Combine. No. Combine, yeah, is one, but compress. No.
Squeeze. Simplify. Is it like a math term?
No, if you want to, like, let's say, it is a math term, yeah. If you have, like, people from outside a society and you want to integrate them into society, put together into the whole so it becomes one. Integrate. So we don't want to use this sum. We want to use a different symbol, S for sum. And this is what Riemann came up with. And he said S for sum, but he didn't want it to be an S. He wanted it to be a more special S. So we just elongated the S into that symbol. Maybe it's more like that. It's basically just that. So it's the sum of fx times dx. Now, how is that how do we integrate? Like we know how to integrate something, and how does it work between two bounds and stuff like that? How does it make sense? Like this is a curve. Why don't we just use the curve? Yeah. Okay. I'm going to try and give you an example where it works to integrate as we know it. To integrate, you have to use a very simple example because it's quite difficult beyond. I'm just going to think about speed, distance, time to explain that. If we say, right, this is time and this is distance on a graph. If we say we have this, and we say this, I want to know the speed between 1 and 3 seconds on this graph. Yeah, we look at the gradient, yeah, and I'll give you the values we have here. Let's say this goes from, let's pick nice numbers that work from us, 80 up to 130. Okay. We can use the gradient here. Yeah, we can use the derivative gradient, or we can just think about it as speed is the distance divided by the time, or gradient. Yeah, you're dead right to use gradient. So the distance would be 130 minus 80 all over 3 minus 1, which is, yeah, 50 over 2, which is 25 meters per second. Okay? Now what I'm going to draw now is I'm going to draw this. So I'm going to draw 25 meters per second in another graph. So I'm going to like draw the gradient function. It's not very interesting. It's that at 25. The gradient function of that. Does that make sense? It's just a straight line between 1 and 3. Okay? Right. Now we have to think about going backwards. So this was the function, and this is the derivative. Yes? Okay. Now I want to think about working backwards a little bit. If I want to find the distance in general, how do I find the distance? Speed multiplied by time, is it? Okay, and in this case I can do that, can't I? What is the time? 2 seconds. What is the speed? 25. Can you see that's the area here? 2 times 25. 2, and it's 25 high. And that's 2 across. So the distance is 25 times 2, which is 50. Okay. Well, let's look back. Where does 50 appear on this graph?
130 and 80.
Between here and here. Yeah, 50 is here. So this is the area here is 50. So the area is represented here. The same area is represented here. Yeah. Between here and here is the same. That's the same. Right.
Kind of like physics.
A little bit.
Don't even say that because then I don't like this class.
Yeah.
Do we ever get tested on like the theory?
No.
behind-
No.
You just need to be able to do it.
This is more interesting than everything. You just need to be able to do it. Yeah. I just find this interesting.
You don't need to calculate movements though?
No.
Yeah.
There's other things you might need to calculate by hand, which is later on, but no.
Like not even
No.
like the 3 different types.
No. I know you'd like to, but.
No, Aiden's not.
Right, but let's say we're only given this. How do we get the area? How do we work backwards? Okay, so yes, we know the relationship between here and here. Let's just say this was fx. What is this one called? Well, there's the maybe Eamon. Who's Eamon? Aiden. Aiden knows what if fx is. If you want to integrate fx, what do you call the other one?
Oh,
We.
it's like a weird.
It's the capital F, like it's the primitive function we use. All right? Okay. So let's say we want to go backwards. I probably shouldn't rub that out. I'll leave that. Anyway, let's say I want to go backwards. We'll remove this for a minute. I want to integrate, I'm using this function now. I want to integrate, or get back up one, the function fx dx. All right. What do I need to do? How do I get it in reverse?
Big F of x is equal to integration.
So I would integrate. I would get the big f of x function, and what would I do? Wait, this specific case now, this was between 1 and 3. In this specific case, what would I have done? Let's say I didn't know 80 and... Let's say I didn't know 80 and 130. How would I get these two numbers? I'd integrate to get the slope, this function. I would put 3 and 1 into the function, yeah. And the area would be the difference between the two. I would put 3 and 1 into the integral and the difference between them. So I'd put 3, the function with 3 and 1 subbed in, and the difference between them gives this area of this shape, yeah? And that's what we do with integration. That is definite integrals in a nutshell. Well, explained. You use the original function, you get the primitive function, which is it's integrated. You sub in between the two bounds you want to find, and then you subtract those two answers because you need the difference between the two to get this area.
And what do they want you to find until infinity?
Oh, we'll look at that later. We'll look at like more difficult. Let's just keep it to simple examples for now. Let's just do it then without any context to the problem and just from what we know. We now know we have to integrate the function, sub in 3, sub in 1, and get the difference. Let's just do it for this one, because we have it up here earlier. What is the answer between 0 and 2? We can integrate now between 0 and 2, lower bound, upper bound. Yeah, and the function is x squared, so x squared dx. And that equals, now how do I write this? There's an in-between step where we can write it as with square brackets. Integrate this, x cubed over 3, are we happy with that? Yeah. I'm going to integrate it, and then I'm going to sub in 2 and 0. Now that's just an intermediary stage between writing this. I'm going to sub in 2, and then I'm going to take away subbing in 0. So 2 cubed over 3, and I'm going to take away 0 cubed over 3. Which gives me an answer of, well, 8 over 3 minus 0, which is just 8 over 3 units. Okay? And that's how you would write it. Usually we write the intermediary step before subbing in, where we showed the integration, and then we're going to sub in between these two bounds. That's how we write that. And then we actually do the subtraction. Let's do some more examples. Maybe slightly more difficult. Not like the integration now is going to start off being quite straightforward. I'm going to do the first one just to kind of prove it again, and then the other ones we can do quite quickly. I'm going to try and do this one with graph 2, 0, 2x plus 1 dx. Let's say, once again, I don't know any integration yet. How would I just get it? 2x plus 1 is a line something like that, maybe. Between 0 and 2. 0 and 2. How would I get the area underneath this curve without... Yep. So I'll make a triangle and a rectangle. Do I know what this point is? That's 1, isn't it? Yeah. Okay. Do I know... Well, I know the height here, do I? So this is y is equal to 2x plus 1. All right. So what's this area? That is 2 in width times 1. So that area is 2 units. What's this area then? You said this goes up to 5, yeah? So that's going to be 3 times 2 divided by 2, maybe? So it's just 3. So this area, the triangle area is 3 units. So together they are 5 units squared. These are squared. Okay, that's using non-integration methods. Now let's remember how to integrate. So 2x plus 1 dx between 2 and 0. Let's integrate. What's this integrated? So it'd be x squared over 2, which we definitely can simplify, plus x over 2 and 0. Question, where's the c gone?
You have a definite
Well, why is there no c?
because
Because
What is the area?
you know the constant because of the area, because of the.
There will not be a constant.
I'm not sure, guys. I'm not sure. I'm going to put in a c. I'm going to put in a c and see what happens. No. Okay, I'm going to put in my c and see what happens. Let's do the same thing. 2 and 0, sub in 2 and then sub in 0. There's going to be a c in here now. That's going to be a bit pain, but we'll deal with it. So these 2's cancel. So it's just 2 squared
The C's can't.
plus 2 plus c minus 0 squared plus 0 plus c. Yes? So this is 2 squared, which is 4, plus 2, which is, yeah, okay. 2 squared plus 2 is, I think we're going to get 6 here. How do we get 2 here?
Oh, you went from 1 to 5, that's 4. If you went 5 is 4, you put 3.
Oh, I did plus 3, yes, my bad.
But I like Kylie.
Haha.
It's not right.
This should be 6, yeah. Okay, anybody watching the video probably figured that out a while ago. 6 plus c minus 0 minus c, yeah? Oh, what happens?
C's cancel.
C's cancel. Is that going to happen every single time?
Yes.
Yes, it'll happen every single
So
time.
then there's no point.
There's no point putting in the c, and that's why we ignored the c here, and that's why you'll always ignore the c in a definite integral, because they'll just end up cancelling it out. They're just a vertical translation anyway. So the answer here is 6 units squared. Same as that, even though we didn't have that the first time. So we should be able to do all these. Let's see, can we get the second bunch?
When you're asking for the definite integral,
Yeah.
is it asking for the area of the integral function or the derivative?
It's asking for the area of this function under the curve. So this would be an x cubed function. So this is might be something like that. And it's saying, right, what's the area here between here and here in the original, not the one above. That's why when we did the speed thing, it's the area of this. It wasn't the area of the one above. Different things. Okay, you do the 3 on the board.